Hello, everyone. Do intrinsic magnetic fields protect planetary atmospheres from stellar winds? This is the topic and the title of a paper that we recently published in Space Science Reviews. And throughout this conference, we've had fantastic presentations about modeling ion escape in the last couple of days, and talks about using measurements as well to figure out what is going on, especially with the mechanics, the physics of what drives ion escape. And our approach to this question is by synthesizing a framework for ion escape and to try and fill that frame with the decades of empirical studies of atmospheric ion escape and solar wind interaction with Earth, Venus, and Mars. And those of you who are familiar with Betteridge's law may think that you already know the conclusion of this talk just based on the title. Now, since all headlines that end with a question mark can usually be answered with no. But as I aim to show you throughout this talk, it's not that simple, neither one way or the other. And what can we hope to gain by comparing ion escape from Venus, Earth, and Mars? Well, these are obviously three very different planets, but crucially, they also share some of their properties. If they were all different in every conceivable manner, then how could we tell which of these properties matter and which ones don't, like magnetization? But by considering the similarities between them as well as the differences, we get some controlled or at least constrained variables. And the inner planets become our laboratory in a way. And if we're interested in developing some model for escape, say as a function of magnetization, atmospheric mass, maybe solar wind dynamic pressure, maybe other parameters used like EUV, then that way we can determine which factors are important and which aren't by constraining the others. And let's start here with Venus and Mars. Both are actually unmagnetized. So that is a property that they share, but they're also significantly different in size and therefore in mass. Mars has only about 1/10 the mass of Venus, and it's only about half its size. So the gravity binding the Venusian atmosphere to its surface is over twice as strong in Venus compared to Mars. Venus and Earth, on the other hand, they have similar size, they have similar mass, and therefore similar gravity. But there is one major difference, of course, in that the Earth's intrinsic magnetic field is, makes a big difference in the way that it interacts with the solar wind. And lastly, we can also think about Earth and Mars, but here we're in a situation where they're different in practically every relevant manner, at least on a global scale. But instead, Mars crustal fields are fantastic for understanding the effects of magnetic fields over a wide range of field strengths, like Tristan was talking about just this morning. And then we've also sent spacecraft to other atmospheric bodies like Titan and to Pluto. But to understand the drivers of such a dynamic system requires a large number of statistics. And therefore, it also requires orbiters. And it may be possible to do some studies of drivers at Titan, but I'm not sure Cassini made enough passes. I think others know more about that than I do. There are also differences in the atmospheric mass and composition, but to first order, think about gravity and intrinsic magnetism as the main planetary properties that can influence the forces experienced by a particle or an arbitrary particle in the planet's upper atmospheres. So gravity matters, and the role of gravity becomes particularly accentuated if we consider the escape energy of a particle in the upper atmosphere. We can easily find the escape velocity for any planet if we know its mass and we know the distance from its center. The escape velocity is the velocity where the kinetic energy of the particle is larger than the work it takes for a particle to reach infinity and escape the gravitational well. And since Venus and Earth have similar masses and sizes, their escape velocities are similar, just about 10 kilometers per second or so. Mars, on the other hand, it has an escape velocity less than half of that at 4.9 kilometers per second. And this means that the energy required for a particle to escape from Venus is about 4 times larger than it is for Mars. And the ratio is about 5 times larger for the Earth. So for example, a hydrogen atom requires 0.6 electron volts to escape from Venus, 0.7 to escape from Earth, and it requires only about a tenth of that of an electron volt to escape from Mars. For an oxygen atom, we're looking at about 10 electron volts to escape from Venus and Earth, but only about 2 electron volts to escape from Mars. And for molecular oxygen, it's around 20 electron volts at Venus and Earth compared to 4 electron volts at Mars. So what I want to get at with this is atmospheric escape from Mars operates under intrinsically different conditions due to its low gravity. And that's something that we have to consider when we do when we look at the trends in escape rate that we get as a function of the upstream parameters and the way that they force the system. So which factor does limit the ion escape rate? Well, the processes that are involved, they're extremely interconnected and dynamic, so they're difficult to model accurately. But like I said earlier, we can treat the planets in the solar system as our personal laboratory for ion escape. And variations in the solar wind and the sun's UV output will do the job of turning the little knobs for us. And all we need to do is to monitor the knobs and measure how the escape from the planet responds. And here I'd like to give a little bit of spatial context. These are maps of escaping ions at Earth, at Venus, and at Mars in cylindrical coordinates, each from different studies, but here shown on the same spatial scale. And when we measure escape rates, it's not sufficient just to measure ion fluxes at each planet. We really need to integrate those fluxes over an area. And the size of Earth's interaction with the solar wind is immense compared to those of Mars and for Venus. And this implies that it intersects more solar wind energy, some of which may or may not be transferred to the ionosphere to power escape. But if we're careful, we can integrate the fluxes over some representative area and find the escape rate to see how it varies with upstream conditions. And people have been estimating escape rates this way for a long time. Here is a timeline of ion escape rates from Venus in yellow, from Earth in blue, and from Mars in red, that are reported by studies that use measurements from spacecraft at each respective planet. And the solar sunspot cycle is shown in green as a function of time. And the horizontal extent is the coverage, the data coverage of each study, and the vertical extent represents the uncertainty that's either reported or that we've inferred from each study based on the time average values that they provide. And as you can see, generally the escape rates from the Earth are higher than those at least reported recently from Venus and Mars, with the exception of 2 studies conducted near solar minimum. And overall, the ion escape rates reported in the modern era are remarkably close for all 3 planets, given the hypothetical range of escape rates that are possible. Generally, the escape rate is in between some factor 10 to the 24 to some factor 10 to the 25. And it's difficult to read out any confident trends in this kind of timeline. The solar activity cycle drives variations both in the EUV output, and it drives variations in the solar wind properties. But with statistics that we get from modern orbiters, many recent studies at least derive ion escape rates for specific ranges or bins of upstream conditions. Now, Andrew Yao and Bill, they really pioneered such studies of the driver's effect on ion escape already back in 1998. That was using Dynamics Explorer data. And based on the escape rates that they got, they derived scaling laws as functions of geomagnetic activity indices, like Kp. And they independently constrained the F10.7 as well, which is a solar wind proxy. This is showing escape rate as a function of Kp. And it would take until 2008 until we had similar scaling laws derived for Mars. And it was only at that point that there was enough data coverage for Mars Express to derive such similar laws. And Lundin et al. Here found a nearly one-to-one relationship between the oxygen ion escape rate and the solar wind dynamic pressure. And these are just two examples, but they illustrate several problems with comparing escape drivers across planets. First, think of the solar wind driver. We have solar wind dynamic pressure in one, and we have Kp in the other. How are you going to compare these two? The other one, we have if 10.7 for Earth, and we don't have any constraints at all for Mars in this case. And number three, we also should consider the difference in energy range. The Earth study goes down to 10 electron volts, whereas the Mars study is about 50 electron volts. So there are all these caveats that are involved when you compare studies between missions, between planets, and over time. And just to give you an example of how this can influence what you're actually measuring, we're going to look closer at what the energy range does. And this is an example for Mars. Here is a spectrogram from Mars Express, which is based on later data that was taken when the ion instrument was patched to be able to measure also down to low energy ions, or down to about 1 electron volts. And the panel on the left here is showing time average measurements of escaping ions that are integrated across the area of the induced magnetotail. Each line is the heavy ion escape rates that's derived for a different range of upstream solar wind dynamic pressure, indicated here in the legend, and with the solar EUV photon flux constrained. The escape energy of O plus and O2 plus are indicated down here at 2 and 4 electron volts, and the 50 electron limit is here at the dashed line. And as the solar wind dynamic pressure increases, well, the amount of escape above 50 electron volts, yes, it does increase. At least that is the case in the Martian tail. But in the case of Mars, that is at the expense of the otherwise intense cold ion outflow below 50 electron volts. So ions are being more energized, and they're also possibly finding other escape channels than just the tail. So the energy integrated flux is shown here on the right, with now the dynamic pressure plotted as the horizontal coordinate. And as you can see, the net effect is, if we only look at this red line, which represents escape over 50 electron volts, yes, we do see this increase, but that's because we're missing the even larger decrease in the cold ion outflow with dynamic pressure. So if you only consider high energies, we're effectively conflating an increase in energization with an increase in ion escape rate. So here is our attempt at making a true interplanetary comparison of solar wind dependencies. We've selected 3 studies based on 3 qualifiers. The study must be likely to capture the full energy distribution at the respective measurement location. It must be looking at the same species as studies at the other planets. It must provide dependencies on the same solar wind parameters as others. And it must also be constraining solar EUV. I think that was actually 4. But in effect, we've chosen to focus on these 3 specific studies because they fulfill those criteria. And in part, there's also these 3 studies because they estimate the dependence of the heavy ion escape rate as a function of a specific upstream parameter, and it's the solar wind dynamic pressure. And they also constrain the EUV. So we're able to see what the increased energy in the solar wind does to the escape rate, while we're largely constraining the rate of ion production by solar EUV. And I know that this is a really busy plot to show in a presentation, so I'm going to break it up for each planet, and I'll guide you through it. This is the ion escape rate for Mars, for low EUV flux shown in black, for high EUV flux shown in red. And as you can see, there's almost no dependence on dynamic pressure, but the escape rates are generally higher when the EUV is also high. This is the ion escape rate from Venus, shown in for low EUV in green and for high EUV in yellow. Masunaga et al., they also divide the ion escape in high and low upstream motion electric field. strength. And we can see that for low motional electric field and high EUV, there is a weak solar wind or positive dependence on solar wind dynamic pressure, but not during low EUV when the motional electric field is high. Also completely opposite to the trends at Mars, the escape rate is generally lower when the EUV is high. The yellow here is lower than the green ones. So despite more ions getting produced, there seem to be fewer ions escaping. And finally, the trends at Earth show that our planet is, our magnetized planet in the trio is extremely sensitive to the upstream solar wind dynamic pressure. During combined low solar wind dynamic pressure and low EUV, the Earth presents some of the lowest measured escape rates. You see down here in the low 10 to the 24. But it really skyrockets with increasing pressure. And that approaches nearly 100 times higher escape rates compared to Mars when the dynamic pressure is high. So ion escape from Earth increases with dynamic pressure like Venus, but the escape rate also increases when the EUV flux is high, just like Mars does. So we have 3 planets with escape rates that display mutually different dependencies on the upstream conditions. And to figure out why, we need to quantify how much energy is being transferred to the escaping ions for different conditions and how this changes the distribution. The solar wind dynamic pressure is the only parameter for which we can try and find escape. It isn't the only one for which we can try and find escape rate dependencies. Here's a comparison of the heavy ion escape rate for Venus on the left and Mars on the right, both as functions of solar EUV instead on the x-axis. In the case of Venus, this is EUV irradiance, and in the case of Mars, this is ionizing photon flux. And as you might notice, despite both of these planets lacking magnetic fields, they display diametrically opposite dependencies on solar EUV. Ion escape from Mars increases with EUV, that's shown by the black dots and fitted function. Those are derived from Mars Express, and the blue line is a result from MAVEN that's shown on a similar scale. And the study by Coleman et al. For Venus shows a decrease in escape with EUV. That's the red line here, the net downtail rate. And that's, as we looked at before, the Masunaga study, they're consistent. They both show this decrease, but we get 3 data points from Coleman. And Coleman also shows really well why the escape rate decreases. The blue line shows only the outward flow, while the yellow line shows only the inward flow. So one part going out, one part coming back in. Now, as EUV is increasing, the Venus ward flow, the yellow line, increases. And that is what results in a reduction of the net escape rate. But it's not the same thing happens for Mars. So that tells us that there's something different between these 2 planets. And
2 minutes left.
Okay, thank you. A recent study by Persson et al. I got a presentation from MOA yesterday talking about this, study the effect of the solar wind on the outward, inward, and the net heavy ion flows at Venus. And in contrast to the effects of solar EUV, a more powerful solar wind has the effect of reducing the Venusward return flows that are shown by the blue arrows here in these panels. This is the escape mapped out in the induced magnetotail for different ranges of solar energy flux. And the increase in solar wind power, if you will, leads to an overall increase in the net escape rate because those Venusward return fluxes are decreasing. And to understand why this happens, we need to understand how the coupling changes with EUV. And I will quickly go through this. This is the coupling actually derived from Mars, but we can consider that 2 induced magnetospheres should display more or less the same dependence. And the coupling in an induced magnetosphere between the solar wind and the ions that are escaping goes down as a function of EUV. That is not the case for Earth. For Earth, well, there is actually no equivalent study for Earth as far as I've been able to find. There are many studies quantifying coupling between the solar wind and the magnetosphere, and the ionosphere, but there aren't many that consider coupling as a function of for EUV with solar wind parameters constrained, and none, as far as I'm aware of, that consider coupling with outflowing ions specifically. So this is a study from Otani et al. It's the closest I've come across. They measured the Birkeland R1 region 1 current as a function of the F10.7 proxy for weak and significantly negative upstream interplanetary electric field, or the motion electric field of the solar wind. And as we can see, the current is increasing as a function of EUV. So that indicates that there's also more power being transferred from the solar wind into the upper atmosphere. But where that energy goes, if it goes into ions or if it goes into neutrals through Joule heating, we don't really know. And we need a framework to try and understand these dependencies. We'll definitely need to quantify the energy of the solar wind that powers the escape, and that may be supplied by DC coupling, DC pointing flux, or AC pointing flux generated by waves. It can be precipitating particle energy. But the energy alone is not sufficient to drive ion escape. In order for an ion to escape, it first has to be produced. And in the inner solar system, photoionization by solar EUV dominates any other production term by orders of magnitude. And most of these ions will be produced at relatively low altitudes where the atmosphere is collisional. Then the ions have to diffuse upwards, in the case of an unmagnetized planet, across field lines without recombining with a free electron. And then they have to make it to the topside ionosphere, where most of the precipitating energy is being deposited. And we can consider this a diffusion rate, and that in combination with the local production rate in the energization region as the supply of ions for escape. And then the ions have to be energized and sent on some trajectory. That trajectory may or may not actually bring them out into open space or return them to the planet. And the key point here is that energy is not necessarily the only factor that influences the rate of ion escape. It's at least a three-step process that requires ionization of neutrals, energization of ions, and an open path to be transported to space without losing that energy. Either of these steps can act as a bottleneck and limiting the number rate of ion escape. I'll skip that and move directly into the framework, and we skip all the complexity of the various mechanisms and just consider the relations between the observed ion escape rates and the effects of upstream drivers on supply and energization. And we can think of the energization rate and supply rates as independent factors. They're building a domain with two main dimensions, an energy limited domain and a supply limited domain. Depending on the intrinsic planetary parameters and the external upstream parameters, we will get an escape rate for an arbitrary atmospheric body that we put there. And that body will then move with, say, solar wind upstream parameters, intrinsic parameters, and so on. And we also get a domain around every planet because the parameters, the upstream parameters, stochastically vary with time around some average value. And while we haven't really quantified the supply or energization rates for any planet, the trends in escape rates and coupling tell us roughly where it should fit in. And comets, they're a trivial case. They lack any significant gravity. That means that the energization rate, which depends on the escape energy in the denominator, is basically infinite. So because the cometary neutrals, they're already escaping. So the only factor that matters for ion outflow from a comet is how many ions can be produced within some defined volume around the comet. And Mars seems to be supply limited. As we increase the EUV, we increase the supply, and we see that it gets to brighter colors, which means that, well, and if we increase the solar wind, it doesn't really do anything because it moves horizontally here, and this color, the escape rate stays about the same. Venus, that's not the case. Even though Venus moves in a similar way, we increase EUV, we go to darker colors, we reduce the escape rate because we increase those Venusward return fluxes. But if we increase the solar wind, we increase the powered rate, so we increase the escape rate. And Earth, seems to work differently when you increase EUV, as we saw those Birkeland currents increase, and presumably some of that increased energy goes into ions, so we get increased escape. And Earth seems to be really sensitive in the way that it couples to the solar wind. So we get a really strong response in the solar wind dependence. And this roughly tells us where these planets seem to fit in. They don't have to be here always. They can potentially, hypothetically, be able to cross into different domains if you get extreme enough events that either planet. And I want to talk a bit about what is missing. We need intercomparable upstream dependencies for Earth, Venus, and Mars. That covers all the escape channels and the same dependent variables with similar constraints for others. So we want to look at solar wind flux, dynamic pressure, energy flux, the IMF clock angles and cone angles, solar EV power, photon flux. We need to quantify ion supply rates. We need to quantify solar wind coupling. We should look at more planetary bodies like Titan. We should look at the effect of obliquity on ion supply and escape. And we really need to understand more than just the escape of oxygen. We need to look also at, say, protons for desiccation and figure out the nitrogen mystery. And to do those, we need to, of course, measure protons and nitrogen from the planets. So I'll leave you with some conclusions in terms of what the state of the systems are, and also an answer to the question. And I'm afraid it's not going to be a straight answer. I don't think we're going to ever arrive at a straight yes or no answer. Do intrinsic magnetic fields protect planetary atmospheres from stellar winds? It depends. Thank you.
Thank you, Robin. We have time for maybe one more question. So there is a question popped up in chat from Injuan. How do we know whether an exoplanet belongs to supply limited or energy limited category? What specific parameters can help determine that?
Yeah, that's a really good question. And I think to try and figure that out, we need to figure out where it fits into this kind of diagram. And we need to calibrate this kind of diagram using the planets that we do have. Say we know the mass of Mars, so we know its escape energy, we know the mass of Earth, we know the mass of Venus, and we know that the upstream parameters of all these planets, and that tells us where they are in this domain. But for now, it's highly conceptual. It's only on a relative sense. We really need to figure out, put some values on these axes, on all three axes, and possibly more. And from that, since we know the intrinsic parameters and the upstream parameters of these, then we can figure out, say, if we have a planet that is slightly heavier than Mars, but has similar, maybe 10 times higher EUV, then we can simply move upwards here in this domain and figure out, oh, it's probably in the energy limited domain if it's this much higher. Or let's say that this planet is much heavier, same thing happens. We move to the left because our escape energy is increasing. And so we move into the energy domain, energy limited domain here. And I hope that answers the question.
Yes, thank you very much. We're a little bit short on time, so we'll have to move on to our next speakers.